Hello and most welcome to H1220. I'm apologizing for the disturbances. I'm actually sitting at the bus here going into the town. Let's see if I can cope anyway, otherwise I'll try and edit the sound. Let's see here if I can't put it in here. I will today talk about decoherence and indeterminism, two major factors in the disappearance of the quantum effects, something that is almost always the problem when discussing quantum mechanics in contrast to the classical worldview. It is often assumed that if you go to a higher enough macro level, the quantum effects will disappear, and usually the explanation for this, yes, decoherence is the magical disappearance of the quantum effects at the macro level. And we discussed earlier, this is a view that is being challenged more and more. Famous names in that region is Carlo Rovelli, Chris Fields, but also Julian Barber, who says the invention of the idea of the disappearing quantum effects is one of the greatest blunders. Well, it could be very good to look into what is the construction of decoherence, and is it possible to assume that the world should follow what we want of the world. There is a famous dialogue between Einstein and Bohr that is completely invented, I think, but still points to the truth of it. Einstein was very upset with quantum mechanics and the very discovery that the world is completely indeterminate was the most gravest thing for Einstein, who wanted to have a classical worldview with existences and so forth. So he should have exclaimed to Niels Bohr, "God does not play dice," upon which Niels Bohr answered, "You cannot tell God what he wants to do." And I think that is very showing between the two worldviews, or the two ways of understanding. I think it's more correct. The Einsteinian way of understanding, which is the classical, is where we tell nature what it should be according to our traditions. One example I often brought up is biology. It's assumed tacitly, indirectly, by biologists until quite recently that for some reason animals, plants, bacteria, microbes, viruses, all should follow the Newtonian laws and not the laws of nature. And of course, it doesn't really make sense when you think about it. Classical physics invented in 1689. Evolution was already finished by 1689. I think the harshest argument there has been that classical physicists are only a stone throw from creationists. They claim that the Earth is just 6,000 years. They claim that the whole of evolution changed magically in 1689 because of Newton's Principia. Well, I won't enter into that argument here. Let's have a look at indeterminism, and if it's true that if you go to a certain level of size and quantity, all of a sudden quantum effects magically disappears. And I mean completely disappears, not statistically disappear, because that is absolutely the case, obviously. So it's a little article here by Chris Fields, and he writes in a simple, direct manner about indeterminism. The problem of indeterminism. Quantum theory has many problems, but the problem that presents the widest gap through classical physics is that of statistical predictions. Classical physics predicts events deterministically. That is, given the present state, you could always predict the next state using a law of nature. In quantum physics, given the present state, we cannot predict the next state deterministically, although we can predict it probabilistically. Furthermore, since we cannot predict the next event, we also cannot explain why it occurs. Yes, it's a problem with causality here, cause and effect. With a loss in predictive ability, we also lose the causal explanation. So I was going to add one last personal comment here, and is that it's not really difficult to see why Albert Einstein had objections, and so many other scientists up to this day have huge objections. It is, in a way, destroying the whole gestalt or experience of a stable, predictable, I would say maybe a world that makes sense in some way, some specific way, I had to say, and where you can predict things, at least in theory, which is very important. I don't think Albert Einstein would have demanded that you actually can predict everything, but that it was potentially possible somehow. Most physicists today suppose that the quantum problem is limited to subatomic particles, and that the macroscopic world is indeed classical. This preferential application of quantum theory to atomic phenomena results in the notorious measurement problem. Where the macroscopic world somehow fixes the state of the atomic world. But in fact, since the macroscopic world is only built from atomic particles, it should also be in an uncertain state. If we suppose that there is a quantum to classical transition, then at what point does this transition occur? Should we treat large molecules with thousands of atoms in them, for example, as classical, quantum, or semi-classical systems? And when does this transition from a statistical to a deterministic world occur? We know that any attempt to overcome the innate statistical nature of quantum theory by adding compensatory hidden variables contradicts quantum theory. In other words, the theory as it stands today, as a theory that uses physical states to explain observations. Very shaky here. See if I can invent something here. I can almost invent something. That's too tough. In other words, the theory as it stands today, it can not be improved, and any attempt to do so will produce contradictions. This result in quantum theory is called Bell's theorem. Addressing the indeterminism, this marks a dead end for an era of thinking that began with Newton and in which all objects behave according to their possessed properties. Now we know that the current possessed properties are inadequate, and any attempt to add new possessed properties will only produce contradictions. We must therefore find a new way of explaining the quantum phenomena, which cannot be based on possessed properties. Conceiving such properties which are not possessed by material objects are yet objective has presented great problems for physicists used to thinking of the world as material objects. And in parenthesis, not my view, the idea of material objects is older than Newton. It dates to around 600 to 700 BC in the Greek tradition. It's a tradition. It's not present in Asia. So, end of parenthesis. This problem, however, need not to be so hard. There is another kind of property which is objective and yet not possessed by the material objects. For example, the mass of a billiard ball is a possessed property of that ball, but whether that ball is on the fifth heaviest object within a collection of objects is not. The latter property depends upon which other objects we are taking into consideration to form a collection. Note that being in the fifth heaviest object is also an objective fact and can be empirically verified. However, that objective fact is not a possessed property of an individual object. Science thus far has dealt with the numbers in a quantitative way, or what mathematicians call cardinal numbers. Those are the numbers that denote size or magnitude. Such numbers can indeed be viewed as possessed properties of individual objects. In measuring such possessed properties, we always define an absolute scale of measurement. This absolute scale, however, does not describe whether the object with a mass of 5 kilograms is the first, the second, the third, the fourth, or the fifth heaviest object. Within a given collection, because we haven't yet defined the collection to determine the relative position. An object can have two kinds of positions, absolute and relational. The absolute position of a mass scale on a mass scale can state that the mass of an object is 5 kilograms, but the relative position may state that the object is the 7th in a collection. Both properties are objective, although the former is a possessed property of the object, while the latter is a property of an object defined in relation to a collection. This means that unless you can take into account the object collection, the relative position of the object cannot be described. Cardinal and ordinal positions. In the absolute definition of position, the object with mass 5 kilograms has the position 5 on the kilogram scale. In the relational definition of position, the object with mass 5 kilogram could have the first, the second, the third, the fourth, or any other position. The absolute definition of position depends only on the object being measured. But the relational definition of position depends on all the objects within a collection. Numbers, when used to denote the relative position, are called ordinals because they describe an order. That is like first, second, third, fourth, fifth, and so on. Current quantum theory describes measurements as cardinal, but not as ordinals. In other words, it can describe the absolute position of quantum objects, but cannot predict the relative order between them. Quantum theory thus predicts the cardinal position, but not the ordinal position. The latter is an objective property too, but it is not a possessed property. Unlike cardinal properties, which pertain to the object being measured, the ordinal properties pertain to an object, although as a part of an object collection. Describing such properties requires the induction of a new way of thinking in physics, where we are describing not just the cardinal, but also the ordinal properties. The interesting part of this problem is that if we know the ordinal properties of all objects, then we also know the cardinal properties of the collection. For example, if you have ordered the object as first, second, third, fourth, fifth, and these are the only objects being considered, and the objects are separated by a mass of 1 kilo each, then simply by knowing the order, you already know the cardinal properties of each of the objects. Thus, if you know that there are 5 objects, but haven't ordered them as first, second, third, fourth, fifth, then you don't know the masses of the individual particles, but you know the total mass. Conversely, if you have ordered them, then you know the individual masses, and by implication the total mass. In short, if you have the order, then you know the quantity, but you have the quantities, then you don't necessarily have the order. This gives us a glimpse into the quantum problem any theory that describes quantities but does not describe the order must be incomplete, because there are many alternative orders. If, however, you have described the order, then the cardinality is already known. In that sense, a theory that describes the order has no need for cardinal properties, although a theory that only describes quantities must always be incomplete. If the description of nature was based on order rather than quantities, then all physical properties used in quantum theory would be unnecessary. Such property could still be used, although their explanation and prediction would be based on ordinal properties. Since the order is always described in relation to a collection, collections would be fundamental too. The quantitative description of nature would be a consequence of a collection and an order that explains quantities better than quantities by themselves. The classical quantum conflict. Classical physics began by describing an individual isolated particle. I shouldn't comment here, but this is very important to remember. Nota bene, remember that it starts there. It doesn't give any hypothesis to support that. It's not axiomatic. They simply started that way. And this is determining. End of comment. When you have only one particle in the universe, only the possessed properties matter. And that single particle is the standard against which its properties would be described. Such a singular particle would therefore be the first and the only particle in the universe. However, when you have a collection of particles, then you must order them after distinguishing them. This order is generally given by locating the objects in space and numbering the spatial locations through a coordinate system. Depending on how you have placed the objects in space and how you describe this space with numbers using a coordinate system, you naturally order the objects by the coordinates. Whether the object is first or the 25th in a collection, therefore, depends on the choice of a coordinate reference frame. Classical physics held that all such coordinate systems are arbitrarily chosen. That is, it doesn't really matter if you call the object first or the 25th, because we are only interested in measuring the possessed properties of the objects on an absolute scale. In other words, the focus of science on possessed properties can be restated quite simply as the arbitrary choice of coordinate system. This arbitrary choice is now formalized in physics as the equivalence of all coordinate systems, whether they are stationary, moving, accelerating. The ordinal position of an object can never be an objective property if coordinate systems are arbitrary. The ordinal position would only be an objective property if there was a preferred coordinate system to describe each object's position. That claim would in turn entail that the notion that coordinate systems are chosen arbitrarily is false. If the missing link in quantum theory is ordinal properties, then the equivalence of all frames is also false. Indeed, the belief that coordinate systems are arbitrarily chosen would directly lead to the quantum problem. We can either have arbitrary coordinate systems or solve the quantum problem, but not both. The arbitrary choice of coordinate systems is called general relativity, and it indeed contradicts quantum theory. This contradiction has presented great difficulties in their unification, which is the greatest unsolved problem in modern physics. It is not hard to see why this contradiction must exist. If we note that quantum prediction require the use of ordinal position, while classical relativity forbids the use of ordinal positions, because they effectively entail that all coordinate system choices are indeed arbitrary. In other words, quantum theory and general relativity can never be unified, because they are based on logically contradictory assumptions. Since we cannot ignore the quantum phenomena, we must explain the premises underlying general relativity in a new way. There are two premises underlying general relativity. One, the speed of light is constant. And two, the formula describing the law of nature is the same everywhere. Both these premises have to be understood in a novel way based on quantum theory. Does light have speed? Let's begin with the speed of light. The notion that light has a constant and finite speed contradicts what is called non-locality in quantum theory, in which two objects appear to interact instantaneously, when the constant speed of light deems this to be impossible. The speed of light and quantum theory are conceptually contradictory, and when quantum theory and special relativity are unified into quantum field theory, infinities are created. To resolve these infinities, a new type of game called renormalization is used, which, according to Encyclopædia Britannica, is the procedure in quantum field theory by which divergent parts of a calculation leading to nonsensical infinite results are absorbed by redefinition into a few measurable qualities, so yielding finite answers. I will not discuss renormalization here, but proceed with assuming that we haven't understood what the speed of light really means in quantum terms. Although we tend to treat light as a quantum particle. The constant speed of light and quantum non-locality cannot be resolved in a single theory, and a new explanation must be found. The quantum explanation of the constant speed of light can be that light indeed takes zero time to travel, but a finite time to be absorbed. When we currently measure as the speed of light need not necessarily be the motion of the photon. It is rather the time taken for the photon to be absorbed. Current quantum theory treats causal interactions quite like classical physics, where it takes particles time to travel from one position to another, but at the point of collision, the energy and momentum transfer is instantaneous. What if light is not like a classical particle and it travels instantaneously but takes a finite time to be absorbed? Both explanations are consistent with the observation, but only the latter explanation makes it possible to solve the quantum problem. How so? The notion that light is absorbed in a finite time entails that the quantum state transition takes a finite time. This transition begins with the source and destination being entangled non-locally, but the effect of this entanglement is seen after the transition is complete. In other words, quantum theory remains non-local, and the so-called locality implied by the constant speed of light is actually a misunderstanding of the quantum interaction created by employing classical notions of causality. Light is therefore not traveling in space and just happens to collide with an electron, changing its state. Rather, the destination of light is already known at the source before the photon is even emitted. The source is therefore not emitting a particle randomly in space, unaware of when or where that particle will eventually land. Rather, the source emits the photon only after it has entangled with the destination, and the particle is always sent to a destination known in advance. In other words, the source of light knows its destination before it emits the photon. The transfer of this photon takes 0 time, but the absorption of this photon takes a finite time. In most cases, in some cases, which are called quantum non-locality, however, the absorption also takes 0 time. Such particles are called entangled in current quantum theory, and rightly so. Two kinds of entanglement. Quantum theory requires 2 distinct notions of entanglement. First, there are particles within an ensemble which are entangled due to the ensemble boundary. If one particle changes state, all other particles must change state simultaneously. Second, there are quantum systems which are not part of the same ensemble, but interact with each other causally, and they must be entangled before the causal transaction occurs. Present quantum theory considers the first type of entanglement, which is called non-locality. But the second kind of entanglement is not adequately understood. The time taken in the second kind of entanglement is due to the time needed to change the state of a single particle. However, if one particle state is changed, then all particle states within an ensemble must change as well. The time taken in the second change is 0. If therefore the entanglement in which the interaction between two systems take time due to the supposed speed of light was understood as the time in readjusting the receiver. There would be no conflict between local and non-local phenomena. The speed of light can therefore be restated as the time of absorption rather than the time of travel. This takes out the first pillar underlying general relativity, namely that light travels and has constant speed of travel in empty space, which Einstein coined because the delay between source and receiver was observed to be always constant. This is actually an observation that is empirically refuted, but we go back to that swiftly. Einstein interpreted the finite time taken from source to destination classically as the motion of some object, thereby creating the non-locality problem, originally coined the EPR paradox after Einstein, Rosen and Rosen, which he himself battled for the rest of his life. This interpretation is perhaps the greatest mistake of 20th century physics, and it's quite unnecessary. If this phenomenon was interpreted in a different way, as the time taken in absorption, then the problem of non-locality, the conflict between quantum theory and general relativity, and the incompleteness of quantum theory would itself not arise. The speed of light is not constant. Empirical evidence now suggests that the speed of light is not constant. Researchers led by optical physicist Miles Paget at the University of Glasgow have, for example, demonstrated the effect by raising photons that were identical except for the structure. The structured light consistently arrived a tad late. We don't have a good explanation for this fact today, and such variations would entail that a number of physical constants would vary as they depend on the speed of light. I would say in general relativity everything is dependent on speed of light, well, with the exception of mass. If this speed isn't a constant, then how must it change the understanding of nature and physics? The idea that light doesn't take time to travel, but takes time in absorption, offers useful alternatives. In this alternative, the time taken to absorb depends on the structure of light, because that structure encodes information beyond the energy of the photon. In other words, we cannot treat light merely as energy without structure. We must rather understand light as something that is described more accurately by its structure. Since light is a vibration, Describing this vibration itself requires assuming a coordinate reference frame and the relation to other objects in that reference frame. If the structure of light is physically important, then a quantum interaction where light has the same energy but a different structure would not produce identical effect, an identical effect. This discrepancy would be caused by the structure, and if we know the light structure, we would not need to know the energy. This takes us back to my earlier point that when science relies on order among the objects, quantity properties such as energy become irrelevant. But there are deeper lessons too in this, which includes the fact that all reference frames are not equivalent, because the source and destination of light must be put in the same frame to even describe the structural effect. The idea that the source or destination are moving relative to each other and therefore in different coordinate frames becomes an impediment, because if we make that assumption, then we cannot explain the structural effect. We are now led to a paradox. There is a sense in which two objects, that is source and receiver, are moving relative to each other. There is another sense in which they are in the same coordinate system. If you tie the coordinate system to the moving objects, you can never ever resolve this paradox. The paradox can only be solved if we say that there is a shared reference frame in which the source and the destination exist. And the moving objects are not moving just relative to each other, but also relative to the reference frame. When this is realized, the second premise underlying general relativity, namely that each object has its own associated coordinate reference frames, also disappears. So the shortest possible summary here is that reference frames have been ignored for a very long time, but they cause a problem in their arbitrariness in quantum mechanics, because it makes the current physics inconsistent. And I am there. So we continue. We have now revealed the rejection of frame equivalence. We now reject all the premises that led to general relativity. One, the finite speed of light, because it contradicts non-locality. Two, the constant speed of light, because it contradicts varied delayed observations. And three, the arbitrary coordinate system choice, because explanation of structure requires a shared coordinate system. Note that we haven't rejected any observation. although we have rejected their interpretations. The finite speed of light is no longer needed if the time taken in a cause effect is in absorption rather than in travel. The constant speed of light is no longer needed because the absorption time depends on the structure of light, and the arbitrary coordinate system is not needed because the structure can be described only in a common reference frame. We are now back to the quantum problem. Without being encumbered by relativistic assumptions, although this problem must now be broadened to include the idea that the absorption of light takes a finite time, depending on its structure, and that this structure must be described in a shared coordinate system. Any two objects that partake in a causal interaction must therefore be placed in a shared coordinate frame. Such objects must be entangled before the energy is emitted, and therefore the light is always headed towards a receiver known in advance. In essence, light is not a particle that collides with other material objects, depending on whichever particle happens to cross its path. Rather, light is emitted with a foreknowledge of which particle will absorb it. We're now back to the quantum problem without being encumbered by relativistic assumptions, although this problem must now be broadened to include the idea that the absorption of light takes a finite time, depending on its structure. And that this structure must be described in a shared coordinate system. Any two objects that partake in a causal interaction must therefore be placed in a shared coordinate frame. Such objects must be entangled before the energy is emitted. Therefore, the light is always headed towards the receiver known in advance. In essence, light is not a particle that collides with other material objects, depending on whichever particle happens to cross its path. Rather, light is emitted with the foreknowledge of which particle it will absorb. New forms of causality. The entanglement between source and destination requires a completely different kind of causality, which is missing in current theory. The succession of particles in the two-slit experiment is therefore due to a succession of entanglements between the source and the detector, and which electron will arrive at which detector is known at the time of particle emission. The particle therefore is not accidentally encountering a destination. rather the particle is destined to a specific detector from the very start. The foresight involving quantum theory is one key reason that makes this theory different from classical physics. But the mechanism of foresights requires a new kind of causality. In the classical way of thinking, if you happen to accidentally meet someone on the road, you would try to explain this based on past states of those objects, and the element of surprise is generally mitigated by supposing that this chance meeting is just a coincidence. In the quantum way of thinking, however, you would say that the meeting was destined and the process of realization had begun much before the event actually occurred. Since we don't understand what was happening before the meeting occurs, we erroneously tend to suppose that the meeting is a chance occurrence. The randomness in quantum theory is quite like a chance meeting with a friend. It appears as a chance event so long as we don't understand how a source and receiver become entangled, which then eventually manifests an event. The entanglement occurs much before the event is manifest, so we cannot observe it empirically. Therefore, we must find new kinds of theoretical constructs to describe this new causality. In classical physics, we are used to thinking that only the present state causes the future state. To address the quantum problems, we now need a new notion of causality in which the past, which is unobservable, creates the future. Unlike the current physical model of causality, this future is commonly called destiny. It exists in the past but cannot be perceived. It entangles with the destinies of other objects to create future events. How this destiny is created, how it entangles with other destinies, and how the entanglement creates events constitutes a radically different form of causality. I will not dwell on these mechanisms here, although I have described them in other places, such as MM. The crux of that explanation is that causal interaction has three parts: cause, effect, and consequence. In the present science, we only study the cause and effect and neglect the consequences. In a new science, material interactions will produce a consequence which remains unobservable until it entangles with other consequences to create an event. The cause of an event is the entanglement between two consequences produced by time. The effect is the event that we observe. And the event produces a due consequence. In short, material transactions create destinies, which lie dormant and therefore unobservable. These destinies are excited into mutual entanglement by time, and that entanglement produces events. The quantum understanding of cause and effect. This view of causality is pervasive across many Eastern philosophy, and in some of these traditions is called karma. In Indian philosophy there are 3 states of karma called Sanchita, Pradava and Kiryamana. The term Sanchita denotes the destinies that lie unentangled and therefore unobservable. The Parabda denotes the destinies that have become entangled with other destinies due to time, and will gradually manifest observable events. The Kriyamana denotes the destinies that are currently manifesting events. From these events, more Sanchita is produced, which lies dormant for a long time. In this way, a cycle of actions and reactions is created, in which the present becomes the past, and the past becomes the future. This view of causality is radically different than used in modern science, but it can be used to understand the problems in modern science. When a person is born or an experimental setup is created, Sanchita becomes Parabda, and the possibility of previous consequences have now become realizable. However, the Parabda will only manifest gradually in a succession of events. The reason we cannot predict these events is because we don't know the Pradabha and how it manifests from Sanchita. We just observe the events, that is, the Kriyamana, and are baffled by their succession. And I think the take here, the most important, is that we seem to, because of the idea that light has speed, that idea that is manifest, and I would say historically that idea has something other than 300 and 400 years to its development. Some of the Greek philosophers did speculate that the light has speed, but mostly it was assumed that light is the world. And quantum physics gets incredibly problematic if we make the hypothesis that light has a speed. It leads to the indeterminism. It also leads to these paradoxical consequences as Bell's theorem, and of course the determinism of Heisenberg. When looking at it closely, we understand that light having a speed is an assumption, and it was an assumption from the beginning. This is not one of those inherited ideas from ancient, but it was actually hypothesized from the very beginning that light did have a speed. But the problem is, to say that light has a speed is using the term speed in a completely different fashion, because light is what builds up the world, it's part of the world. and to say light has an origin, like the bus I'm sitting on currently, it has a start and it has an end point. This is not true of light, not even in general relativity. Making that assumption puts a very spooky idea to the universe in itself. It is like a dark universe, and you need light in that darkness to sort of point into all things that exist in the world. So first you have objects, you even have destinations, you have relations, and then all of a sudden you open up light, so you can put light on the situation and reveal everything. This is not how it works at all. Light is not like a lamp, or the idea of going into a dark room and lightening up the room with a lamp. No, light is always already there. It is part of the structure. And taking something that is derived, which you can say the speed of, for instance, a vehicle or a bullet, and comparing that to the speed of light, then you're already into a whole bunch of problems. Chris Fields has written a lot about how the tremendous change in the idea of what cause and effect is during the 18th, 19th century is one of the factors has led to the baffling misunderstanding of physics nowadays, and it has entered into everyday language. Just as in the case with time, most people today have the cause and effect that was created during the 18th century, not the previous one that actually was much closer to the true cause and effect of quantum mechanics. Instead, we are now using a Newtonian, sort of an oversimplification of cause and effect that neatly fitted the mappings and drawings of Isaac Newton in his study chamber. But those are hypothesized. They are not part of the world as such. And as Niels Bohr once said, being stuck in the Newtonian world is an everyday experience. Because every time we say time, space, relations, cause and effect, we are using Newtonian or pre-Newtonian notions of those things. And those understandings are indeed problematic because they block out the predictive power that we used to have, and that led to the passivity of modern man. I think I'm closing my destination. I think I'll round up here. The last thing, the take on this is absolutely the arbitrariness of coordinate system. Both classical physics and general relativity and specific relativity assumes that how you represent the thing is not important at all. The world still will remain the same. And that assumption has never ever been argued for. It is just tacitly assumed. And that causes the idea of forgetting the reference frame. But if you forget the reference frame, you forget everything. The reference frame is something you construct individually, subjectively. And I have to quote my old physics professor, nobody are any longer interested in physics as they used to be, because they all choose very subjectively, very individually, their own point of reference frame, and they're constantly doing that. And this of course has led to the modern death of physics. Nobody any longer know about physics and science because of this problematic forgetfulness of reference frame. You can never ever forget reference frames. This is of course what the son of Niels Bohr so vehemently and persistently claimed. Don't bring mysticism into our classroom. Classical physics is based on mysticism, and it makes everything highly emotional and subjectivized, whereas quantum mechanics take the reference frame into consideration at every single observation and experimentation, and therefore causes objectivity. And objectivity these days is incredibly rare. It has never been rarer since the demise of the Newtonian model. I say thank you very much and have a very pleasant afternoon. Bye bye for now.